Hi everyone and welcome. I'm Purnima Pandey, Marketing Manager at TestMu AI, and I'll be your host for this session, Beyond Scoring, Rethinking, Ranking in the LLM Era at the TestMu Conference 2026. It's so good to have all of you with us. And before we begin, a quick note for all of you. Please share your takeaways from this session on LinkedIn or X, tag us, and use hashtag TestMeConference so the wider community can join the conversation. And if you have questions along the way, you can drop them in the Q&A box, and we'll definitely take them at the end. Ranking systems were built on carefully designed objective functions and years of tuning. But models can now reason, understand intent, and read natural language. That changes what a ranking objective can even look like. So here's what we're delving into today. When you put an LLM into a ranking system, what to do? What do you gain? What do you give up in latency and validation? And which of today's approaches will actually hold up in production? Please join me in welcoming Rhea Goel. Rhea is an applied science manager at Amazon. She leads the development of large scale machine learning systems for ranking, recommendation, and personalization. Her work covers applied AI, production ML, and LM powered systems. Today, she'll draw on recent research and public industry work to look at rankings as a set of engineers' trade offs. Ria, thank you so much for giving us your time today. The stage is all yours.
Thanks, Purnima. Hey, everyone. I'm Rhea. And yes, as Purnima mentioned, I'm here to talk about how I think we are fundamentally changing ranking systems with the advent of LLMs. So, we've spent the last 2 decades building increasingly sophisticated ranking models, but LLMs introduce a completely different way of expressing objectives, reasoning about intent, and optimizing rankings. So, today I'll walk through what changes and perhaps most importantly, what doesn't. And I hope to provide a conceptual overview of how LLM based ranking systems are evolving from ideas emerging in research to the patterns that we are beginning to see in production. So let's start with a simple example. Imagine three people type the exactly same query into a hotel search engine. So the first person is traveling for a conference. They're probably optimizing for things like proximity to the venue, reliable Wi Fi, breakfast, flexible check in. The second person is traveling with a toddler and elderly parents. So suddenly those priorities change completely. Now they're looking for family rooms, maybe a quiet neighborhood. And the third is a backpacker who might be optimizing for price, nightlife, proximity to public transport. So, what's the correct ranking? The answer is all three. Ranking has never been about finding the single best item. It's about finding the best ordering for a particular user and context. And that is the central challenge of production ranking. So we aren't optimizing for a single objective, we're balancing many competing objectives simultaneously. Relevance, business goals, diversity, price, ratings, and so on. So how do we solve this today? So in a modern ranking system, we don't rely on a single model. We first retrieve a manageable candidate set from millions of items. That's the first stage ranker. Then predict signals like relevance or engagement. And then finally, a re ranker applies additional business objectives and constraints before producing the final ranking. And this architecture scales extremely well and has served the industry for years. The challenge is when product requirements become increasingly nuanced. So imagine the product manager says, hey, prioritize hotels that are great for families unless quality drops significantly while still encouraging discovery without hurting long term engagement. Now, every part of that sentence sounds perfectly reasonable, but somewhere now an engineer has to translate this into a mathematical objective function with different thresholds and optimization weights. And that's where things become difficult. So these weights come from offline experiments, parameter tuning, countless A B tests. But as we said, as objectives become more nuanced, the translation becomes difficult. So, which raises an interesting question. What if, instead of translating human intent into objective functions, we could just optimize for language directly? Now, this is what LLMs make possible. So we just simply describe what we want. No weights, no equations, no handcrafted optimization function, just intent expressed in natural language. Now, that's incredibly expressive, but it immediately raises several engineering questions. Can language be optimized reliably? How precise is unless quality drops significantly? Or can models reason consistently? Can we trust these decisions? And how should we evaluate them? So, those questions form the rest of this talk, and I'll walk through how the research community and the industry are beginning to answer these questions. So, for that, let's maybe take a short exercise where we want to replace a traditional re ranker with an LLM. So, where do we begin? There are really five things to ask. If we have a general purpose LLM, is prompting alone enough? If not, how do we teach the model about our domain? And once it understands our domain, how do we refine its behavior to capture more nuanced preferences? And then, how do we make it fast enough for production? And finally, how do we know whether it's actually better? So let's tackle those one at a time, starting with the simplest possible approach, which is prompting a base model. So we start with the general purpose LLM. We give it a simple prompt. Hey, you're a hotel ranking assistant. Rank these hotels for an anniversary trip to Napa and explain your reasoning. And the response actually is quite impressive already. So without any additional training, the model understands concepts like romance, vineyards, luxury, memorable experiences, and it correctly infers that a boutique vineyard resort is probably a better fit than a business hotel. This is something traditional ranking models struggle with because they don't have access to broad world knowledge. So the first impression here is, hey, this already looks pretty good. But would you deploy it tomorrow to production? Probably not. So one of the reasons is that our behavioral data actually tells a slightly different story. Users planning anniversary trips may still book the Marriott instead of this boutique vineyard. Why? Because maybe they're familiar with the brand. Maybe they have loyalty points. Maybe they prefer a lower price point. Maybe they want flexible cancellation. So none of these preferences were mentioned in the prompt, and many of these aren't things that the model could infer from world knowledge alone. So this highlights an important distinction. A base LLM understands language remarkably well, but it doesn't yet understand our platform and our users. That's something we have to teach it. And that's the key difference between traditional behavioral models and LLM based rankers. Behavioral models learn from millions of historic interactions. They're really good at predicting what the users are likely to do. So, for example, they can learn that families consistently choose the hotel with the free shuttle to Disneyland, even if the query never mentions a shuttle. So, but LLMs excel in a different way. They reason from language. So if someone's asking for a romantic anniversary getaway, they can infer that a boutique vineyard hotel with a spa is probably a better experience, even without historical interaction data. So these models, they aren't exactly solving the same problem. One predicts behavior, the other reasons about intent. And in practice, modern ranking systems increasingly combine both. So the key point here is that one is not better than the other. They just solve different problems. Behavioral models capture implicit preferences revealed through user behavior, while LLMs capture explicit intent expressed through language. So, how do we teach the model about our own platform? This is where supervised fine tuning comes in. The prompt tells the model what the task is that we're solving. Rank hotels by booking likelihood, but the labels teach it what booking likelihood actually means on our platform. So, across millions of examples, the model gradually learns patterns such as brand familiarity matters, loyalty programs, influence booking decisions, users often trade luxury for affordability, or free cancellation increases conversion. So, it can learn these things through these examples. Um, and this should feel very familiar. Conceptually, this is exactly what traditional learn to rank models do. The difference is that the supervision is expressed as complete ranking examples rather than engineered features. But optimizing for historical behavior isn't always what we want. Suppose the user explicitly says, hey, we don't mind spending more for a memorable experience. Now, the fine tuned model still tends to recommend the Marriott because that's what historical booking data suggests. But if you ask a human for this query what they would prefer, they're more likely to say the boutique vineyard resort because they have incorporated context that goes beyond the average historical behavior. So, this is where supervised learning reaches its limits. Sometimes we just don't want to imitate the past. We want to teach the model what people believe is the better decision in a particular context. So that naturally leads to preference data. So so we basically ask annotators to to compare two rankings. So instead of producing a perfectly ranked list, which is surprisingly difficult, we simply ask them which is better. And they're more consistent at comparing two alternatives than producing a full rank list. So these comparisons capture subtle judgments that historical logs often miss. Like the user explicitly said they're willing to spend more, that the experience matters more than the average behavior, things like that. So this preference data that we collect lets us encode those nuanced judgments. Um, so this is where preference optimization comes in. So fine tuning imitates the historical behavior, but preference optimization refines the model using higher quality judgments about what the ranking should be. So how do we actually train the model from those preferences? Um, the most common answer to that is reinforcement learning with human feedback, or more recently, AI feedback. So it separates learning into two stages. First, we collect human preferences and train a reward model to predict which rankings people prefer. And then we use reinforcement learning to then optimize the LLM so it produces rankings with a higher predicted reward. The key idea is that the reward model becomes the learned objective function. And once we've learned that objective, we can repeatedly improve the ranking model against it. Uh, this produces remarkable results for instruction following LLMs, but it also introduces a great deal of complexity. So naturally, researchers asked, hey, is there a simpler way to optimize for preferences? And uh, can we get the same benefits with a simpler optimization procedure? And that's exactly the motivation behind a new technique called direct preference optimization. So instead of explicitly learning a reward model and then running reinforcement learning, DPO just optimizes the language model directly from the preference pairs. So conceptually, it's very simple. We increase the probability of preferred rankings and decrease the probability of rejected rankings. And in practice, we find that DPO actually achieves quality comparable to reinforcement learning with human feedback on many tasks while dramatically simplifying the training pipeline. So let's pause one time. So we now have a ranking model that understands our domain through supervised fine tuning, and we have refined it using preference optimization. We've shown how it can reason about multiple objectives while still satisfying constraints. Now, the next question is, given this trained model, how should we use it to produce a ranking at inference time? Uh, oops. Okay. Sorry about that. Um, okay, so up until now, every example that we've looked at has optimized a single objective, which is identify the best hotel for this user and query. But that's not how production systems work. Um, if you've ever worked with a product manager, you know what happens next. Hey, can we also optimize for affordability? Can we also promote new inventory? Can we promote sustainable hotels? And don't hurt revenue. So, so what these let's look at what these objectives actually mean. So here, there's a lot of ambiguity to these. So prioritize family-friendly hotels unless quality drops significantly. How much quality are we willing to trade? Is a 4.5 rated family-friendly hotel preferable to a 4.8 rated family hotel that is not family-friendly? Or like when we say prefer walkable hotels, what is walkable for you may not be walkable for me. Or like stay within my budget of 250 if possible. When is exceeding the budget acceptable? Is 260 reasonable, or is 290 okay? So these are things that are underspecified, but that's the advantage of natural language objectives, that they're expressive. So how do we ensure to address these? So some of these are hard constraints where we ensure that we don't let the LLM try to satisfy them. We just enforce them deterministically either before or after LLM re-ranking. But then there are some soft constraints where the idea is not to actually eliminate the ambiguity, because that's where the power of LLM comes in. We actually don't want to eliminate the entire ambiguity, but we just want to make sure that they are consistently reasoning across requests. For that, we typically, as before, we do human preference alignment through things like DPO, and we constantly evaluate the model. So let's pause again one more time. So now we have understood how we can optimize for multiple objectives with some guarantees through preference alignment. Um, so now the question becomes, is the how do we make LLMs fast enough to run in production? Every component here is improving ranking quality, but it introduces additional computation. Larger models require more GPU memory, longer prompts increase context processing, reasoning generates more output tokens, and multi-stage pipelines increase end-to-end latency. So how do we make these systems more efficient without giving up most of the quality? So the first question is, can we use a smaller model? And that's like, do we really need a 70 billion parameter model for every ranking request? Many ranking decisions are relatively straightforward. So if a smaller model could produce similar rankings most of the time, we could just dramatically reduce latency and infra cost. That leads us to our first efficiency technique, which is knowledge distillation. It should again feel familiar because once again, we're just doing supervised fine tuning. The difference is that instead of humans creating the labels, we can ask a much larger and more capable teacher model to generate them. And the teacher reasons through the ranking problem and produces both a ranking and potentially an explanation. And these outputs become training examples for a smaller student model. And we repeat this a bunch of times offline, and then in production, we deploy the student model. So this allows us to retain much of the teacher's capability while significantly reducing inference cost and latency. Another technique that I don't mention here is routing. So you can actually have online make a decision on whether this query is complex enough to need a language model or a reasoning model. Um, and then another is cascading, where you first have a smaller model handle the query, but if you think the output doesn't meet the bar that you need, then you have it cascade to a more complex model. So then another is, can we reuse computation? This is something that actually now comes out of the box. So it's called prefix caching. Notice that the two requests here have different users, different hotels, but the system prompt is identical. So in many production systems, that shared prefix can be over 1,000 tokens long. So rather than processing those 1,000 tokens for every request, the serving engine caches the model's internal state after processing that prefix once. So when a new request begins with the same sequence of tokens, the serving engine detects that match and restores the cached model state instead of recomputing it. So the model itself doesn't know this is happening. This is an optimization that happens entirely within the serving infrastructure. And now most serving engines actually come with this out of the box. So it's not something that you as a practitioner have to implement. And then this is the thing that I was talking about earlier. Does every query need the same reasoning capability? Some queries are incredibly simple, others require more deeper reasoning. So that's where routing and cascading come in. Okay, so finally, uh, we have a ranking model, understands our domain, aligns to our preferences, can reason about multiple objectives, And we've made it practical to deploy at scale through distillation, prefix matching, and adaptive inference techniques. So now we've covered the complete life cycle, but how do we know that it's actually better? So how do we evaluate reasoning? So traditional ranking metrics like NDCG, mean reciprocal rank, precision at K, they remain extremely valuable. They tell us whether the model produces rankings that agree with, you know, historical relevance judgments or human relevance judgments, but they don't tell us why a model preferred one ranking over another. So with LLMs, we also want to make sure that we are making sure that the reasoning aligns with the human preferences and explanations. So one uh, so you can imagine for a human to evaluate an LLM response would be very taxing. So instead of asking humans to compare thousands of these rankings manually, we ask another LLM to evaluate them. So we provide the user query, the candidate tells, the ranking produced by our model, and an evaluation prompt. So the judge model then evaluates the ranking against the explicit criteria. So important thing here is that the criteria is also written in natural language. So rather than producing a simple score, we can ask the judge to explain its reasoning and evaluate multiple aspects of the ranking quality. So let's look at this example. Notice three important components. Um, One is an evaluation rubric. So we give it exactly we spell out the criteria that we want, so the judgment is consistent, and then we ask it to explain its reasoning. That's chain of thought. It is known to make sure it is known to uh, show that the LLM can more consistently reason about things if we ask it to explain the reasoning. And then at the end, we want to give it a structured output so that the judgments can then be programmatically pooled, aggregated over several examples. um, so let's step back, look at the complete picture. We have discussed how to teach the model through fine tuning and preference optimization. We have um, seen how to combine semantic reasoning with some deterministic constraints. We have tried to make the system practical. And finally, we've discussed how to evaluate both the rankings and the reasoning using traditional ranking metrics along with LLM as a judge. And taken together, these components form the life cycle of a modern LLM re-ranking system. I'd like to conclude by stepping back from the individual techniques and discussing the broader design principles that connect them. So I think of these as four engineering tensions. Um, and so the first one is prediction versus reasoning. So traditional ranking models excel at predicting user behavior from historical interactions, while LLMs introduce semantic reasoning that captures intent and context beyond those behavioral signals. The next is precision versus expressiveness. Natural language makes it much easier to express ranking objectives, but production systems still require precise guarantees through constraints and structured outputs. The third is generality versus controllability. So foundation models bring remarkable general knowledge, but they must be aligned with specific objectives, policies, and requirements of our platform, of our production ranking system. And the final is quality versus cost. So larger models and deeper reasoning, they improve ranking quality, but they also increase latency and infrastructure cost. So production systems continually balance these objectives through techniques like we mentioned, um, like distillation and adaptive inference. But yeah, overall, I think these four tensions provide a useful framework for thinking about not only today's systems, but also where the field is heading. Uh, So let me leave you with one final thought. We often ask whether LLMs will replace traditional ranking models. And after working through this entire life cycle, I don't think that's the right question. I think the more interesting question is, how do we combine the strengths of both? One gives us efficient statistical prediction, robust infrastructure, and decades of production experience. But LLMs, they provide semantic reasoning, natural language objectives, and much richer ways of aligning models with human preferences. So the future of ranking might not be about choosing one over the other, but about designing systems intelligently that balance these complementary capabilities. Thank you. I'll leave you here with the reading list. Okay, that's all I had.
Thank you so much, Rhea. Okay, my camera. Sorry. Thank you so much, Rhea. That was really, really interesting and highly insightful. And I'm sure all of our attendees and the viewers have really enjoyed it. We have a lot of questions in the Q&A box, so I'll start taking them. Uh, Paul asks us, could an agentic AI model also serve as a production re-ranking model, or would that be more would that be more capably than it is needed?
Um,
Can you
I'm not.
also see it on the screen?
I
It's
do. I
also
do. Okay, maybe I'm not fully sure I understand the question, but say I'll assume by agentic AI model we mean some agent that is capable of multiple things. And I think yes, in the production world, we do kind of need more agentic style models because we have different parts of the um, so the example I gave you, for example, actually let's take another example. So someone's looking for in an e-commerce setting, looking for dresses that they can wear to a wedding in Hawaii. You kind of need skills for the model to actually go look up, hey, what's the weather like in Hawaii? Or, hey, what are some dress archetypes or styles that one wears to a wedding as a guest? What colors to avoid? Don't wear white to the wedding. So you need a bunch of these things that need to be answered, and these could be different, say, there could be something that's talking to the database, something that is actually doing the reasoning. So there could be like multiple components. So yes, I would in general say that yes, that's how I would think about production re-ranking also.
So another question from Bharat. He asks, could an agent that makes humans more effective be considered successful even if it completes fewer tasks autonomously?
Um, I'm assuming this is not related to ranking. um,
So
I think yes. I think
yeah,
in general, yes, an agent success criteria could be that it is helping um, automate some human task end to end. I wouldn't say it's not successful if it can do everything. I think any efficiency gain is good. Yeah.
okay. Uh, so how do we decide what makes an LLM answer better when two answers can both be correct?
Yeah, this is actually a good question. This is actually a common challenge. This is a practical challenge that everyone faces. The the best way that the industry has been solving for this is direct preference optimization. So we actually get pairwise preferences from humans. We train an another LLM model to mimic the human annotator to become that judge. And then we can expand our preference data set. And then we can do direct preference optimization to have the LLM mimic the human preferences. So the idea is that um, you want, so say if as a human, I know a rubric, I know what makes an answer better than the other, then I can provide that in the prompt. But there are times where it is hard to articulate what is better. That's the time when you actually just ask humans, hey, which do you prefer? And then let the model learn it.
Yeah. Uh, So another question from Paul. He asks if do you anticipate new tools on the horizon that may serve as a ranking agents more efficiently and accurately than say ChatGPT?
Oh yeah, absolutely. I think there's already if you go through this reading list that I shared, there's already a bunch of um, tools and models and techniques that have been developed specifically for the ranking application that are built on top of all these foundational models. And there's also, as I mentioned, the productionization challenge with most ranking systems. They're usually sub-second latency requirements for any ranking problem that I can think of. And typically you would use things like distillation, smaller language models, and all of those. So you'll see in a lot of these papers that I listed here, a lot of these mentioned that are actually pretty commonly used.
Great. So just moving on to the last question now. While traditional ranking models undergo scheduled retraining on fresh engagement data, continuous improvement for an LLM driven ranking loop is less straightforward. Does it rely primarily on prompt refinement, fine tuning, the base LLM on specialized ranking datasets, or periodically updating a smaller distilled model?
That's actually the answer is right there. It's all three. In practice, you kind of do all three. I would say um, most systems that I have seen in practice or read about online, they're still hybrid. They still have the traditional ranker plus some LLM re-ranker component. And so anything that the continuous improvement basically continues on both sides. And for the traditional ranker, we have a scheduled retraining on new engagement data. Similarly, for the fine tuning component of the LLM re-ranker, we would have a similar cadence. And then prompt refinement is also something that can be actually automated. So there's some recent developments in the industry where people are actually building agents that can evaluate the CX continuously and then provide reasoning of, hey, this is not looking good, or hey, this could be better. And you can actually provide that as input to your LLM to ranker. So that's actually another emerging area that's coming up.
Great. Thank you so much, Rhea, for that deeply illuminating conversation today. I am really, really glad to be a part, to be a host of this conversation, and to have met you and been here through this session. It was a wonderful session. Thank you so much for being here with us. To our audiences, I would like to say let's keep the conversation going on social media. Don't forget to tag us and share your learnings using hashtag TestMuConference. Also, my apologies to everyone whose questions were not picked today. We shall definitely answer them in our YouTube videos or in our upcoming blogs. And also, you can watch and pull up these recordings anytime from our YouTube channel, just in case if you ever need to. It was a great time, Rhea. Thank you so much again for being with us. Happy testing to everyone. Enjoy the rest of the conference.
Thank you. Thanks all.
Thank you, Rhea.